Okay, so we've talked about the Bronsted-Lowry definitions of acids and bases, and right now there's this question that I want lingering around in the back of your head, which we just addressed at the end of the previous segment. How do we know when substance X is going to act as an acid or a base? Okay? For now, let's sort of put that aside, just keep it on the back burner, and let's consider a few situations where I'll clearly tell you something's going to act as an acid or a base. And first, just become comfortable with that and see if that doesn't help us start to figure out a few things intuitively for ourselves that we can use to answer the question in general when we encounter a new compound, whether it'll be an acid or a base. All right? So let's look at some acid-base reactions. For example, HBr plus water. When we put hydrogen bromide into water, hydrogen bromide possesses an H. That means it could act as an acid, all right, or should act as an acid. Water possesses an H as well, though. Maybe it could act as an acid. Right? So there's a scale that we're going to learn about that tells us who has the greater desire to act like the acid in this situation. And so we're going to get access to that scale when the time comes. And I know in advance from having seen the scale that HBr is the substance that is able to act like the acid, meaning that the water will act as the base in this situation. So what does the acid do? It donates a hydrogen to the water. That's going to turn water into, you have to add a hydrogen, so it's now H3O, and you add a unit of positive charge, because that's what the proton is. It's an H with a plus charge. So your recipe is always adding one more hydrogen and increasing the charge by 1 unit. Okay? What's left behind from the HBr then is just the Br, but it has to have a minus charge now. So that we have totally a neutral situation on the right side, no charge net, just like we had no net charge on this side here. Now I've used a reversible reaction because we know now, having just finished chapter 14, that all reactions are reversible. So if we jump to the right side, the product side, and consider how would we get from this side back to that side, all right? It would also be an acid-base reaction. In this case, the H3O is the only species that can act as the acid. It's the only thing that has hydrogens on it. So it's the only thing capable of donating. And Br minus with a negative charge is only set up to accept. So both sides of an acid-base reaction feature an acid and a base. And more than that, there are connections among the pairings. The base, water, has turned into an acid. And the acid, HBr, has turned into a base. This is a pattern that exists in every acid-base reaction. Okay? So the acid always, if you want, turns itself into a base. Okay. We actually have a name for that base, that partner of the initial acid that you start with. It's what we call the conjugate base. Whereas a base will turn itself into an acid. And the acid that it becomes, we call the conjugate acid. So HBr/Br- is what we refer to as a conjugate acid-base pair. And actually, H2O, H3O plus is another conjugate acid-base pair. Every acid-base reaction will feature two conjugate pairs. Right? And there are important relationships among the partners in a pair. So we'll need to know about these pairs as we move through this chapter. It'll be something you want to quickly be able to determine. And if you need information, for example, if you have information about bromine, because it's got a partner, you also have information about HBr because they're connected to one another in this relationship. Right? So that's sort of down the road a little bit. Okay, let's look at a different acid-base reaction. The phosphate ion with water. Okay. Let's see if we can figure out, without me telling you, what the products of this reaction would be. Okay. Look at PO4 3-. The question that you want to ask yourself right now is, can this act as an acid or a base? Or which way can it act? Because it lacks hydrogen, the conclusion is it cannot act as an acid, right? And it's forced to act as a base. If it's the base, then by default, water must act as the acid. Now this, when we introduce acid-base chemistry, often confuses students. In the example that I just wrote up, I labeled water as a base. Now I'm labeling water as an acid. All right? And many people would say, wait a minute, is it water neutral? Right? They know something about the pH scale and the fact that it should have a pH of 7. All right? Well, we're going to get to all of that, all of those things. All right? But so for right now, we're just focusing on this really broad idea of behavior. And we could go back to the list that we generated a few minutes ago, actually in the previous segment, of Bronsted-Lowry acids and bases, and water could now be added to both lists, just like there were a few compounds that showed up in both lists. Water can act as an acid or a base. Right? I'll come back to that in a minute and how that happens. Right? But once we've settled on the identity of each thing as a reactant, that helps us figure out the products. If water's the acid, it's going to donate one and only one. And that's going to be an important implication for all our work in this chapter. Nicely, our reactions are always going to have coefficients of 1. Right? And in the last chapter, perhaps some of you struggled when the coefficients of the reactions were 2s and 3s, and you had to remember in your reaction table to have 2x's and 3x's, and then you had to square and cube your concentrations in your equilibrium constants. These problems are beautiful from one perspective because all the coefficients will be 1. We're going to limit ourselves to 1 proton transfer at a time, regardless of how many it looks like it could transfer total. All right, it always happens one at a time. All right, so if we move one proton away from water, water becomes OH with a minus charge. So we've taken away something positive. And the PO4 gets the H, so we put that out front. And its charge moves from 3 minus up to 2 minus. Again, if we considered how would we get back to the left side? Well, to get back to the left, the HPO4 would give away its hydrogen. That would mean it's the acid on the right side, and OH minus is the base. And our pairing is water with OH, PO4 3 minus with HPO4 2 minus. So those are our conjugate acid-base pairs. Now, even without a reaction, we should be able to recognize what the conjugate partner of a substance is. Okay? So let's identify, just practice a few of these, the conjugate base of each acid. So I'm telling you this list of things that I'm going to write up, each of them is going to act like an acid. They might be able to act either way, but we want to say when they act as an acid, what is their conjugate base partner that they turn into? H2SO4, HCO3 minus, HC2H3O2, and we've already seen it, but we'll put it down here again, H2O. Sorry, left out a word again. We're identifying the conjugate base. So after a reaction has occurred. So acid, again, defines a behavior. Donate H+. So you get rid of one H+ from each of these substances, and what's left over is your conjugate base. So to take away one from H2, I've got HSO4, and I'm going to have one less unit of charge, so that's going to have a 1 minus charge on it. HCO3 minus will become CO3 2 minus. This guy, C2H3O2, has lots of hydrogens on it. It's only the one out front that is capable of being donated. If we drew the line structure of this molecule, one of the hydrogens is different from all of the others. That's a key thing to look for in molecules. If nothing else, you've got no clue about what's going on, look at a molecule and see how one thing might be different from others, because that's usually going to dictate the behavior that you're seeing. These 3 hydrogens are all attached to a carbon, whereas this one is attached to an oxygen. So that makes it different. That makes it the one that's going to be donatable or donated away to another substance. Okay? And so that's written out front, actually, even though I've got it at the tail end of my molecule. We write it out front sort of as the cation to let you know it's the one that you take away. So C2H3O2 1 minus. And again, water becomes OH minus. Any questions on identifying or coming up with the conjugate base of each acid? Let's flip it now. let's identify the conjugate acid of each base. So this list will be acting like bases, and we're going to add hydrogens to them. CH3NH2. HCO3 minus. PO4 3 minus, and water. You could actually work from the bottom up on this set pretty quickly. We've already seen when water acted as a base in our first example of an acid-base reaction and it gained a hydrogen, it became H3O plus. We had PO4 3 minus in this example right up here. So it becomes HPO4 2 minus. HCO3 minus, we had it over here acting like an acid, but it's a middleman, so to speak. It can go either way as an acid or a base. So when it acts like a base, it's going to gain another hydrogen. So that would be H2CO3, and it's now neutral because the positive coming with the proton cancels that negative there. So the trickiest one in this group is this methylamine, CH3NH2. We're going to add a hydrogen. So the question is, where do we stick it in the formula? Okay, so this is just to sort of show you. Usually you add it to the nitrogen because that's where the lone pair of electrons is. This molecule this is the only open site for the hydrogen to be attracted. Okay? And so anytime you have a nitrogen in a molecule, it usually has that lone pair of electrons, and that's going to be the site of acceptance of your proton. So we would write this CH3NH3 plus, like that. So those are our conjugate acid-base pairs. We want to quickly be able to turn an acid into its conjugate base or a base into its conjugate acid, because we're going to do a lot with them in our acid-base reactions. Any questions on any of those so far? Okay. That'll conclude the second segment then.
It's good stuff. It's only 18 minutes. Oh, they'll be so happy. Only 18 minutes.
It didn't stop.
Oh, it didn't stop. No!
Cut that out. So.